A very common application of exponential functions is compound interest. We're going to take a look at an example, which is $1,000 invested at 5% compounded annually. What compounded annually means is that at the end of each year, so once each year, the interest is added to the principal and interest starts accruing on the interest. So this is different from simple interest, which is sort of more of a mom and dad loan model where they're not really trying to make money on you, right? In a simple interest model, you're always just paying interest on the principal regardless of how much money you owe at any given time. Or if it's working in the other direction, you're always earning interest only on the principal regardless of how much is owed to you at any given time. So what we want to do here is in the first year, it's just like simple interest because it's not until the end of the first year that we start to compound. So we're just going to add 5% of $1,000. Well, one way to add 5% is to say we started with 100%, we got 5% more. So after that 5% increase, we are at 105%. This way, we can just multiply by 1.05 to calculate that percentage or that percent increase. So I'm going to calculate this by multiplying by 1.05 and bring in a calculator, and we'll see that 1,000 times 1.05 gets us a 5% increase on $1,000. So that's 1,050. It's the same thing we would get if we had just calculated 5% of 1,000 and then added it, but we'll see why it is that we're interested in doing it this way. In the next year, I'm going to take 5% of the 1,050 and add it to the 1,050. So that means I'm going to multiply by 1.05 again. And bringing the calculator back in, we get 1050 times 1.05 is 1102.5. So I've already made $2.50 more than I would have on the simple interest model. And the further out we go, the more difference it's going to make. I'm going to multiply this by 1.05 one more time to get the end of year 3, 1157 point, let's say 63 cents. We'll round this to the nearest cent. So now we've made $7.63 more than we would have under the simple interest model just by multiplying by 1.05 at each step instead of just adding $50 at each step, which is 5% of the original 1,000. So we can see from this now, since we know how to construct an exponential model from a y-intercept, which is 1,000. So my y-intercept is 1,000, and my base, A, is 1.05. I can see how to construct a model for year t. This is just going to be my y-intercept of 1,000 times 1.05 to the power t. So this compound interest is an exponential model. Now I can figure out in year 20, right, quickly without having to multiply by 1.05 over and over again by just using a power button on my calculator. So let's see how much we would have after 20 years. So this is going to be 1,000 times 1.05 to the power 20, which gets us 26.53 and 30 cents. Note that the simple interest model, the linear model, after 20 years would get us up to $2,000. It would just be $50 a year for 20 years, so that's $1,000 in interest plus the $1,000 that we started with. So the difference between the exponential model and the linear model increases as we go out farther in time. For other types of compound interest, we have a more sophisticated formula which allows for compoundings more frequently than once a year. Once a year is still, while it's a big improvement over the linear simple interest model, it's still not very frequent compounding. So this formula allows us to compound interest n times per year. So n is the number of compounding periods per year, which means we need to think about what kind of language is going to come up. If we're compounding annually, that means once a year. That would be n equals 1, and that's equivalent to what we just did, that we figured out from first principles. Quarterly would be 4 times a year. Monthly would be 12 times a year. There's other words like maybe you'll see semi-annually coming up every now and then, right? Semi-annually really means twice a year. But most of these we can figure out. If it were weekly, we'd want to use n equals 52. If it were daily, we could use n equals 365, right? But these are the ones that come up the most frequently. So that gives us our value of n. We have to just take it from the wording. In this example, a principal of $1,500 is invested at a rate of 6.5% compounded quarterly. The word quarterly is our clue that n is equal to 4. The rest of the problem gives us some of the other variables. $1,500 here is our principal, P, and we're asked after 5 years. That's giving us a value of t. And by the way, time is always in years with this formula. The number of compounding periods per year suggests that time is in unit of years. And our 6.5% interest, annual interest rate, needs to be converted to a decimal. So I'm going to write this as 0.065, moving that decimal point 2 places to the left. So I'll plug in everything I have to this formula. It looks like I don't know A. How much is present? That tells me that A is the amount that I don't know. So I'm going to leave A as a variable and start plugging in. A is equal to 1,500 times 1 plus 0.065 over 4 to the power 4 times 5. I'll do a little bit of simplifying on this, but I mostly want to let the calculator do it. I don't want to do any rounding. So the 0.065 over 4, I think I can evaluate that without any rounding. 0.065 over 4 comes out to 0.01625, so I'm going to write this as 1.01625. And yes, I do want all those digits because we're going to raise this to the power 20. So any rounding that I do now is going to have serious rounding error in the next step. I'm not only going to raise it to the power 20, I'm then going to scale it up by 1,500. So rounding that seems like it's out in the thousandths or 10,000ths place is really going to be maybe even in the tens place after finishing this computation. So we really don't do a lot of rounding along the way. I'm going to now punch in 1,500 times 1.01625 to the power 20, and I get 2,070 and 63 cents.